Welcome to today's class. Today's main result is this theorem that you are seeing in your screen, which, given a Fuchsian group gamma, a locally finite fundamental domain for gamma, and a non-identity element, provides a type of subset of the hyperbolic plane with shape naturally defined in terms of the type of Mobius transformation taken, and satisfying that despite not necessarily being always compact, it has the property that only finitely many of its images on their gamma intersect the topological closure of the locally finite fundamental domain D. So let's start with some elementary considerations, kind of mainly mainly aimed at separating the notions of, being only finitely many images, the ones that meet this topological closure, and being only finitely many elements of gamma having the property that the corresponding images meet this topological closure, right? I mean, so let's do some a couple of more or less concrete examples. So suppose we have an infinite cyclic Fuchsian group, so that either all its non-identity elements are parabolic Mobius transformations, or all its non-identity elements are hyperbolic transformations. So in the parabolic case, we draw here the fixed point. In the hyperbolic case, let's say that these two are the fixed points of all non-identity elements. And in the parabolic case, if all non-identity elements of the group are parabolic, let's assume that this is a fundamental domain where for certain pair of shortest curves passing through the fixed point which lies at infinity. And in the parabolic case, if all non-identity elements are hyperbolic, let's assume that this is a fundamental domain for some pair of shortest curves, right, which are then orthogonal to the unit circle, and also orthogonal to all the segments of a Euclidean circle passing through the fixed points. Okay, in the parabolic case, we take any horocycle, let's say open horocycle, or even any horocyclic region based at the fixed point. In the hyperbolic case, we take a hypercyclic region passing through the fixed points, and by hypercyclic region, I mean the region contained or determined. The connected region determined by any pair of distinct segments of Euclidean circles passing through the fixed points. So like this. Okay, and then here you see you can take either just the open horocyclic region, if you will, or the closed horocyclic region, just realizing that when I say closed horocyclic region, I would mean closed as a subset of the hyperbolic plane, so it would not contain the fixed point, right? Because the fixed point is not in the hyperbolic plane; it's a point at infinity. Which means in particular that even if I say that I take a closed horocyclic region, that closed horocyclic region is not compact, right? Because this fixed point is not in that closed horocyclic region, right? Okay, and similarly here, even if I say the closed hypercyclic region, it would be closed in the hyperbolic plane as a subset of the hyperbolic plane, but it would then not contain the fixed points, which means that even if I take the closed hypercyclic region, that closed hypercyclic region would not be compact. Okay. Okay. Now, of course, let's say that my parabolic transformation, the parabolic transformation which generates the group gamma in this case takes the points in this shortest curve to the points in this shortest curve, right? So like for instance, this point goes to this point, etc. Right? Like this to this to this, etc. Right? In other words, that somehow it moves in this direction, right? So then somehow the image of this shortest curve is some other shortest curve, and the image of this new one is another one, etc. Right? So somehow this is a fundamental domain, and then we have this other different fundamental domain, this different new fundamental domain, etc. Right? And so you can even see you can already see the cyclic structure of the group, because somehow the iterations, you can see them, right? The the first power sends this to this, the second power this to this new one, the third one to this new one, etc. Right? Okay. Now notice the following. This horocyclic region, either the open one or the closed one, which, as I said, would not be compact, either of them is stable on the action of all elements of the Fuchsian group, right? I mean, why? Because we already saw that each horocycle is stable under the action, right, or invariant under the action. Okay. So this means the following, that when I consider this horocyclic region, and I consider the set of all its images under the group gamma, that set of images has only one element, namely the same horocyclic region. Right? So, in other words, when I consider this set, let's say sigma of K, where K is the horocyclic region, with sigma varying inside gamma, this one is just K itself, right? So it has only one element. Which this in particular implies that when I consider the set of all the images of K with the property the property of meeting the topological closure of the fundamental domain, this set, well, you see, it's again just K. I mean, of course, it's contained here, right? But it's easily seen that it's just K. Right? Okay. On the other hand, if instead of speaking of the images of the horocyclic region, I consider the set of the sigmas with the property that the image of K on their sigma meets the topological closure of the fundamental domain, this set of elements of gamma is gamma itself. And this is pretty much because this one is stable on their this region is stable under the action of gamma, which is infinite cyclic. Something similar happens in the hyperbolic case. If I consider this hypercyclic region, which is stable under the action of gamma, what I see is that because it is stable, the set of all images, any image is actually K itself. So this set of images is actually just K itself. Whereas when I consider the elements of gamma that make it meet D bar, that is the whole of gamma. Right? For instance, let's say that I want to show that that the inverse of gamma, the inverse of this generator that sends this shortest curve to this other shortest curve, is in this set. Let's try to show that the inverse is there. So you see, take the image of this one on the generator, on the generator gamma. Let's say that it's this one. You see, and then here is some part of K with the property that when I apply the inverse, I land in D, right? So see, my inverse is there, and so on, right? So let's say that I want to show that the square of the inverse of the generator is there. So take the image now here, right? And here you have some part of K with the property that when you apply this one, then this one, so the square of the inverse of the generator, you land in D, right? So okay, and so on, right? So that's how you show that gamma, that this is the whole of gamma. Okay, and now let's move on to the theorem. Right? So we take a Fuchsian group gamma, we take a fundamental domain, and we assume that it's locally finite. Okay, and now given any element, if it is elliptic, we consider the hyperbolic disk with center the fixed point, and you can actually take this to be either the open or the closed disk of any positive radius. Okay, and what the theorem states is then that the number of images of K that meet D bar is finite. Now, in the parabolic case, what we take is a horocyclic region, any horocyclic region, based at the fixed point, and again we can take it closed or open. Just noticing that even if we take the closed horocyclic region in the hyperbolic plane, that closed horocyclic region doesn't contain the fixed point because the fixed point is not in the hyperbolic plane. So it is even in that case, even if we take it closed, it is not compact. Okay, but still the number of images that meet D bar is still finite. And in the hyperbolic case, I take the hypercyclic region, take a hypercyclic region based at the two fixed points. So recall that it's determined by two segments of two segments of Euclidean circle passing through the fixed points. And in that case, with the same warning that even if we take the closed hypercyclic region, that closure doesn't contain any of the fixed points because the fixed points are not in the hyperbolic plane, so it cannot be compact. But nevertheless, the number of images under gamma that actually meet D bar is finite. Now, so you see, in the statement of the theorem is you see, if you give me if this one is locally finite, if the fundamental domain is locally finite, whenever you give me a non-identity element, there is certain type of set with the property that only finitely many of its images meet D bar. And actually, like at least one image meets D bar. These parts, the parts that that at least one of the images meets D bar, is it's very easy because you only need to pick. You see, if you give me any element of K, I mean, in all of these cases, it's clear that it's not empty. K is not empty. Take any element, and then there is some gamma that puts it inside the bar, and then you are done. So this part is actually follows immediately from the fact that D is fundamental domain, and you don't even need the local finiteness property. Okay, and now the elliptic case is quite simple, and it's because K is closed and so compact. So this just follows from the local finiteness of D. So let's move on to the harder cases. Actually, the hardest case is the parabolic case, and it is hard because when you take any horocyclic region and you consider the action of the subgroup generated by gamma on that horocyclic region, and take a fundamental domain for that action, right, in the horocyclic region, that fundamental domain is not compact, right? So, like, even if you take even if you take the closure and you include this bounding Euclidean line, even then the closure of this fundamental domain is not compact, so that makes it hard to use the local finiteness of D. So one needs a trick. One pretty much needs kind of in a way, as we will see, is a way of kind of forcing the fundamental domain to be compact, or rather kind of just kind of focusing on only a part of it and kind of ignoring a good chunk of the horocyclic region. That's what we're going to do. Now, without loss of, we are going to work in the parabolic case. We're going to work in the upper half plane, and up to conjugating with a Mobius transformation preserving U and sending the fixed point of gamma to infinity. We can assume without loss of generality that that the fixed point of gamma is actually infinity, right? So that we take a lot of control on the shape, on the description of the horocyclic region. Namely, we are taking the open horocyclic region, so it's determined by a positive constant K, right? So it's the set of all z's that lie above this horizontal Euclidean line. Okay, now, because you see now everything takes the form. I mean, we see that we are in the situation of the result from the previous lecture, because now we know that the lower left entries of the elements of the Fuchsian group do not accumulate in zero, right? So that there's a positive constant with the property that all those matrices that that do not have a zero here have the entry bounded by that positive constant, right? I mean the absolute value, so sufficiently far away of zero. Okay. Now let's notice this. If we take an element not in the stabilizer of infinity of the fixed point of gamma. Well, we have this imaginary part. We computed it a long time ago, and it's equal to this in terms of the imaginary part of the original z. Writing z as x plus iy with x and y real, we compute this, right? I mean, this one just becomes y, and the square norm is this number. And now y is positive, and when we add to this positive number non-negative number, we can only increase, but then when we take a multiplicative inverses, we can only decrease. So I have this less or equal than this, where here I'm no longer writing this one. And that is because before dividing by the number, this one is less or equal than the other one, right? Okay, now this one here I can cancel y, right? And you see, because of this, I have this other kind of reversed inequality. But this one I can replace again y with this, right? It's y is the imaginary part of z. So we notice this. You see, for every element not in the stabilizer, every nu would be mu of b, and every element of u. What we see is that if this imaginary part is greater than this number, then you see, then I apply this. I mean, I know that this one is less or equal than this one, but you see, this inequality implies that 1 over it is less or equal than, you see, the kind of inverted. Okay, so yeah, but here this cancels, and I obtain just 1/2, but this 1/2 is definitely smaller than 1. Okay, so this means that, you see, in this new Hypercyclic region, right, where I'm above k plus 1 and above this number, and you see, I just put k plus 1 kind of just in order to actually hit a Hypercyclic region contained in the original one. That's all. But kind of my main point is that in this new Hypercyclic region, k naught, which kind of looks like this one here, right? I mean, here is somehow my original one, and inside it I'm taking a smaller Hypercyclic region. What I see is that for any element here and any element not in the stabilizer, I have imaginary, the imaginary part of the image is never 1. That is, you never hit I with elements not in the stabilizer. Okay, but with the elements in the stabilizer, which are the only elements remaining, with those ones we also don't hit I, right? Because here you see greater than k plus 1, so I is not here, and this one is closed on these horizontal translations, so you never hit I, right? So you never hit I with anything in gamma, right? Regardless of whether that anything is in the stabilizer or not. So this means that this union, well, of course, is contained properly in the upper half plane. But you see, this means in particular that with the gamma translates of k naught, you cannot cover the whole of u. So V bar cannot be contained in any of these, right? Because if it were contained in one of them, then this would cover the whole of U, because V bar contains a fundamental set. Okay, so this means that Right. Not for there doesn't exist any translate of K naught containing D bar. Okay. So you see, this means the following. Suppose we have an element of gamma with the property that the corresponding translate meets K naught. So that we have a point in K naught. Well, we know then that image, right, has to contain some point outside K naught, right? Because of this, right? I mean, notice that this inclusion is equivalent to this inclusion. So in particular, there does not exist any nu with the property that this is contained in K naught, right? So for any nu, there must be some point outside K naught, some point of D bar, some point of the corresponding image outside K naught. Okay, so we have a point. We would have a point inside because of this condition, and there must exist a point outside. Right? Now there must be a point outside, a point of nu of D bar outside K naught, but here still here in K. Why? Because otherwise nu of D bar would be contained, well, in this part here, but there must be some part here, and it would be disconnected. But D was connected, so D bar is connected, right? So we see that for such an element with this property, this has to meet also this part, right, by connectedness. And here is the description of that part. Okay, now you see this here. That's kind of the trick. That every time I hit K naught, I hit this kind of smaller part. So somehow this part kind of still big enough so as to have to be kind of essential to meet the images of D bar, if you will. Okay, now inside K1, now I take a fundamental domain for the action of the subgroup generated by gamma in K1. Okay, so that I should, well, it's the closure of some fundamental domain there. So I have this, right? Okay, but also E is compact. So the set of elements of gamma that make D bar meet E is finite, right? Okay. Now I go into the proof of the statement of my statement, namely that that the number of images of K that meet D bar is actually finite. So all what I've done so far is only preparation, is kind of only the trick I need to be able to extract a compact set and kind of, a compact set that is still kind of big enough, right, and kind of well compartmentalized in terms of the subgroup generated by gamma and the rest. Right? Okay, now suppose I have an image that meets D bar, an image of K that meets D bar, an image of the horocyclic region that meets D bar. Then because of this property, nu of K1 must meet D bar, right? I mean, just apply kind of nu inverse here. So, okay. But then you see, then the thing is, apply. You see, this has to be not empty. So take a point there, apply nu inverse. That nu inverse of that point is in K1, which is equal to this. So so for some power of gamma, I have gamma inverse of nu inverse of the point in the intersection that lies in E. So what I obtain is that for this nu with this property, what I see is that for some power of gamma, I have this property. So this means that this element of gamma has to be one of these elements of gamma. So it's one of them. Okay. Right, but then you see, now solve for nu. And what I obtain is, well, nu of k is equal to sigma inverse gamma n of k, but k is invariant under horizontal translations. It's stable under all horizontal translations. So this is equal to k. And what I see is that this image, right, is equal to this image, right, for some element in this finite set. So I'm done. And here you can clearly see that kind of the statement is really about the images and not about the elements that can put k, that can make k meet the bar. Okay. So I'm done, right? Because I have this containment and S is finite. Okay, now let's move on to the hyperbolic case. In this hyperbolic case, is easier than the parabolic case because in the hyperbolic case, when I take the intersection of this fundamental domain, I mean, when I take a fundamental domain for the action of the subgroup generated by the element gamma in the hypercyclic region, that this one, its closure is already compact, and that didn't happen in the parabolic case. So that's why in the parabolic case I needed a trick to kind of shrink this fundamental domain for the action of the subgroup generated by the element gamma in the holocyclic region. I needed to shrink it to a compact case. Here I don't need to shrink it. Here already the closure is already compact, whereas here it wasn't. Okay. So it's going to be easier. Okay, again, up to conjugating the whole gamma, the whole Fuchsian group gamma inside PSL2R, I can assume that the fixed points of my hyperbolic element are 0 and infinity. And actually, like up to conjugating, if necessary, again, once more by transformation in PSL2R exchanging 0 and infinity, I can assume that gamma is given by multiplying by some constant greater than 1. Okay, and then I assume here, maybe I shouldn't say must, but I assume that the hypercyclic region has this form. I mean, a hypercyclic region, as I said, is a region determined by two segments of Euclidean circles common to the fixed points, right? That passing through both of the fixed points. When I move, in the case, these are 0 and infinity now, so these have to be circles in C bar passing through 0 and infinity. Well, they are just straight lines passing through, Euclidean straight lines passing through 0 and infinity. Okay, and I'm just going to take the horocyclic region. Let's say here I'm just taking it symmetric with respect to the imaginary axis. Well, okay, but now the point is, you see, I take a fundamental domain for the action of the subgroup generated by gamma in the hypercyclic region, close it, so I have a compact set with the property that translates on their powers of gamma cover the whole hypercyclic region. This is obvious. This one is compact, so the number of elements of gamma that make d bar meet E is finite. And I'm done. I mean, it's now it's the same argument as before, right? So take nu with the property that this image meets d bar, and so we again have this for some power of gamma, right? I mean, take a point in this intersection, which I'm assuming non-empty, and apply nu inverse. So you land in K, and once you land in K, then you can move to E by some power of gamma. But this implies that the transformation itself is an element of S. Okay, and now solve for gamma inverse and use the fact that the hypercyclic region is stable under the powers of K of gamma. And so I'm done, right? Because now I can see that this image of K is equal to this image of K, and it's controlled by a finite set. Okay, so I'm done. To close, to finish today's class, let's prove a useful corollary, which says that if you give me a Fuchsian group, and you take a locally finite fundamental domain, and whenever you give me a fixed point of a parabolic element of gamma, so any fixed point of parabolic element of gamma, then it is possible to move that fixed point into some closure of D. Into the closure of D by some element of gamma. And of course, since I want to move this point, which is not in the hyperbolic plane because it's a point at infinity, since I want to move it into a closure of D, well, I have to take the topological closure inside C bar, not in H, right? Because points at infinity are not in H. So let's prove it. We work again in the upper half plane model. Again, without loss of generality, I assume that the fixed point is infinity. Okay, and that the stabilizer then is consists of horizontal translations. Okay, now take any horocyclic region based at Z0, which is infinity. Okay, and take any sequence of elements of K tending to infinity. So their imaginary parts go to infinity. Okay, so something that happens, something we know since D is a fundamental domain, is that there exist elements of the group that move these points inside inside D bar. And so what we obtain is that this intersection then is not empty, right? Because all of these lie in this intersection. Okay, so following, you know, to kind of tracing the proof of this parabolic case here, what we see is you see that up to some powers of gamma, I have those elements are in S, right? Which is finite. So there exist these integers so that they all give me the same element of S. Why the same? Because S is finite, right? So okay, so because S is finite, so there must be an infinite repetition. Right? Okay, and now solve. So you see, for each of them, let's say to consider this equality, you can solve for nu J2, right? Kind of move things around to express nu J2 in terms of nu J1, and the same manipulation allows you to write nu JL in terms of nu J1 for all L. Okay, and once we do that, we apply nu JL, which then to set JL, which as we saw is in D bar. So this is in D bar, but now express this ZJL, right? Okay, but so you see now this is for the very same transformation, nu J1, and you see the point is that the imaginary part of this number is the same as the imaginary part of this number because this one is a horizontal translation. Okay, so what we see is that all of these are in D bar, and when this one tends to, and you see when this tends to goes to infinity, then I have to be in the topological closure in C bar, right? Because all of these are in D bar. So I'm done. Right? So nu J1 of infinity has to lie in the topological closure of D bar in C bar.